Right now, as you're watching this video, you're hurtling through space at 67,000 miles per hour. But here's the crazy part. Despite that mind-bending speed, you're still trapped. We're all trapped in what scientists call our cosmic prison, orbiting a star that holds us captive with invisible chains of gravity. And for the first time in human history, we're actually planning our escape. But escaping our solar system isn't like packing a bag and catching the next flight out of town. We're talking about breaking free from gravitational forces so powerful they could crush you into atoms, crossing distances so vast that light itself takes years to make the journey, and developing technology so advanced that it makes our current rockets look like paper airplanes. The engineering challenges are so extreme that some scientists believe it might be physically impossible with the laws of physics as we understand them today. Yet despite these seemingly insurmountable obstacles, there are brilliant minds working right now on breakthrough technologies that could make interstellar travel not just possible, but inevitable. We're standing at the edge of becoming an interstellar species, and the timeline might shock you. Some experts believe we could see our first serious attempt at leaving the solar system within the next 20 years. Others think we're already closer than most people realize. I'm about to walk you through the 3 most promising methods scientists are developing to escape our cosmic neighborhood, reveal why traditional rocket engines will never get us there no matter how powerful we make them, and show you the mind-blowing physics behind the technologies that actually could work. But first, let me prove to you just how impossibly difficult this challenge really is by showing you what we're up against. The solar system is absolutely massive in ways that our brains simply cannot comprehend. If Earth were the size of a marble, the Sun would be a beach ball sitting 26 yards away. But that's not even the crazy part. The edge of our solar system, where the Sun's influence finally weakens enough that we could consider ourselves truly free, would be over 1,000 miles away from that beach ball. At the scale of a marble Earth, you'd have to drive from New York to Denver just to reach the boundary of our cosmic prison. Now imagine trying to throw that marble hard enough to reach Denver. That's essentially what we're trying to do with spacecraft, except the physics are even more brutal than this analogy suggests. Every single object in our solar system is locked in an intricate gravitational dance with the Sun, and breaking free requires achieving what scientists call escape velocity. For Earth, that's about 25,000 miles per hour just to break free from our planet's gravity. But to escape the Sun's gravitational grip from Earth's distance, you need to be moving at over 42,000 miles per hour relative to the Sun. Here's where things get really interesting though. Our fastest spacecraft ever built, the Parker Solar Probe, has reached speeds of over 430,000 miles per hour. That sounds incredibly fast, and it is, but there's a catch. It achieved that speed by falling toward the Sun, not away from it. When you're trying to escape the solar system, gravity becomes your enemy instead of your friend. The Voyager probes, which are currently our only human-made objects that have actually left the solar system, took over 35 years to cross the boundary, and they're still moving relatively slowly compared to what we'll need for true interstellar travel. But speed isn't even our biggest problem. Distance is the real killer. The closest star to our Sun, Proxima Centauri, is about 4.2 light-years away. That means light, the fastest thing in the universe, takes 4.2 years to make the journey. At the speed of our fastest spacecraft, it would take over 70,000 years to reach our nearest stellar neighbor. That's longer than all of recorded human history, twice over. This is why conventional rockets, no matter how advanced we make them, will never be the answer to interstellar travel. Chemical rockets work by burning fuel and shooting hot gas out the back, which pushes the spacecraft forward. It's basic Newton's third law. But here's the fundamental problem that cannot be solved with better engineering. The amount of fuel you need grows exponentially with the speed you want to achieve. To go twice as fast, you don't need twice as much fuel. You need dramatically more. Scientists have calculated that to accelerate even a small probe to just 10% of the speed of light using chemical rockets, you would need a fuel tank larger than the entire solar system. That's not an exaggeration. The math simply doesn't work. Chemical rockets have taken us to the Moon, to Mars, and throughout our solar system, but they've reached their fundamental physical limits for interstellar travel. This is exactly why the most brilliant minds in physics and engineering have been working on completely different approaches. Technologies that sound like science fiction, but are based on real, proven physics. And some of these concepts are far more advanced than most people realize. The first breakthrough method is called ion propulsion, and it's already being used successfully on spacecraft today. Instead of burning chemical fuel, Ion drives work by using electricity to strip electrons from atoms, creating charged particles called ions. These ions are then accelerated to extremely high speeds using magnetic fields and shot out the back of the spacecraft. The individual ions don't weigh much, but they're moving incredibly fast, which means they can provide thrust for months or even years without running out of fuel. The Dawn spacecraft used ion propulsion to visit 2 asteroids, Vesta and Ceres, and it worked beautifully. The thrust is incredibly gentle. If you held an ion engine in your hand while it was running, it would feel like a piece of paper pressing against your palm. But that gentle push can operate continuously for years, eventually accelerating a spacecraft to speeds that chemical rockets simply cannot match. Current ion drives can accelerate spacecraft to about 200,000 miles per hour, which is already faster than any chemical rocket has ever achieved. But scientists are working on advanced versions that could reach even higher speeds. The key advantage is efficiency. While chemical rockets burn through their fuel in minutes, ion drives can operate for decades using just a few pounds of propellant. However, even advanced ion propulsion has limitations for true interstellar travel. The speeds we're talking about would still require thousands of years to reach nearby stars. That's better than chemical rockets, but it's still not fast enough for human interstellar missions. Unless we're willing to send generation ships where multiple generations of people live and die during the journey, we need something even more revolutionary. This brings us to the second breakthrough method, and it's probably the most exciting development in propulsion physics in the last century. It's called fusion propulsion, and it promises to unlock the same energy source that powers the sun itself. Fusion rockets would work by forcing hydrogen atoms to combine into helium, releasing enormous amounts of energy in the process. This is exactly what happens inside stars, and the energy density is millions of times higher than any chemical reaction. A fusion rocket could theoretically accelerate a spacecraft to 10% or even 15% of the speed of light. At those speeds, a trip to Proxima Centauri would take only about 30 to 40 years instead of 70,000 years. That's still a long time, but it's within a human lifetime. More importantly, it's fast enough that we could send robotic probes that would return data while the scientists who launched them are still alive to analyze the results. The physics of fusion propulsion are well understood. We know it works because we can see it working in the sun every day. The challenge is engineering. Creating controlled fusion reactions requires temperatures of over 100 million degrees and pressures that are almost impossible to achieve and maintain. Scientists have been working on fusion power for decades, and we're finally reaching the point where controlled fusion might become practical. Several major breakthroughs in fusion research have happened just in the last few years. In December 2022, scientists at the National Ignition Facility achieved fusion ignition for the first time in history. They created a fusion reaction that produced more energy than it consumed, proving that controlled fusion is possible. Private companies are now racing to develop commercial fusion reactors, and many experts believe we'll see the first fusion power plants within the next 15 to 20 years. Once we master fusion for power generation on Earth, adapting it for spacecraft propulsion becomes much more realistic. The engineering challenges are still enormous, but they're no longer impossible. A fusion-powered spacecraft would carry hydrogen fuel and use magnetic fields to contain and control the fusion reactions. The high-energy particles produced by fusion would be directed out the back of the spacecraft, providing thrust that could accelerate the ship to a significant fraction of light speed. But here's where things get really wild. There's a third method that could potentially get us to nearby stars not in decades, but in years or even months. It's called light sail propulsion, and it works on a principle that most people don't realize exists. Light has momentum. When photons hit an object, they actually push on it with a tiny amount of force. This force is incredibly weak, but it's real and it can be amplified. A light sail is essentially a giant mirror attached to a spacecraft. When light hits the sail, it pushes the spacecraft forward. The acceleration is extremely gentle at first, but unlike chemical rockets that burn through their fuel quickly, light is free and unlimited. A spacecraft with a light sail can continue accelerating as long as it receives light from a star or a laser. The really exciting version of this concept involves using powerful lasers on Earth to push small robotic probes to incredible speeds. The idea is to build arrays of lasers that can focus enormous amounts of light energy onto ultra-lightweight spacecraft equipped with highly reflective sails. These spacecraft would be accelerated to 15% or 20% of light speed in just a few minutes of laser bombardment. This isn't science fiction anymore. There's a real project called Breakthrough Starshot that's working on exactly this technology. The plan is to launch thousands of tiny spacecraft, each weighing only a few grams, toward Proxima Centauri. These spacecraft would reach their destination in about 20 years and beam back the first close-up images and data from another star system. The engineering challenges are significant. The spacecraft need to be incredibly lightweight but still carry cameras, communication equipment, and computer systems. The laser array needs to be powerful enough to accelerate the probes, but precise enough to keep the laser beam focused on targets that quickly become smaller than specks of dust. And the communication systems need to work across interstellar distances with very limited power. But every single one of these challenges is being actively worked on by teams of scientists and engineers. The physics are solid, the technology exists. What we're really talking about now is optimization and refinement, not fundamental breakthroughs in our understanding of physics. What makes light sail propulsion even more incredible is that we've already proven it works in space. The Japanese spacecraft Icarus successfully demonstrated solar sailing in 2010, using nothing but sunlight to navigate through the solar system. More recently, the Planetary Society's LightSail 2 mission showed that a small spacecraft could actually raise its orbit around Earth using only the pressure of sunlight. These weren't just proof-of-concept experiments. They were functional demonstrations that light-based propulsion is ready for serious development. But here's the part that will blow your mind. Scientists have calculated that with current laser technology, we could theoretically build a system powerful enough to accelerate a probe to 20% of light speed within just a few hours of launch. Imagine that. A spacecraft leaving Earth and reaching speeds that would get it to Alpha Centauri in about 20 years, all powered by lasers that we could build today if we had the funding and political will. The Breakthrough Starshot project isn't just dreaming about this, they're actively developing the technology. The plan involves building an array of lasers with a combined power of about 100 gigawatts. That's roughly the output of 100 nuclear power plants, all focused into beams that would hit spacecraft no bigger than computer chips. These tiny probes would carry cameras, basic scientific instruments, and communication systems that could transmit data back to Earth across interstellar distances. The timeline for this project is aggressive but realistic. Engineers believe they could have a working prototype system within 15 to 20 years if development continues at the current pace. The first interstellar missions could launch in the 2040s, with data returning from Proxima Centauri in the 2060s. That means people alive today could witness the first detailed exploration of another star system. But light sails have limitations too. They work best with very small, lightweight payloads. We're talking about spacecraft that weigh grams, not tons. That's fine for robotic reconnaissance missions, but it's not going to work for sending humans to the stars. For crewed interstellar missions, we need something different entirely. This is where the physics gets truly mind-bending. There are theoretical propulsion concepts that could potentially transport human crews to nearby stars in reasonable timeframes, but they require mastering physics that we're only beginning to understand. One of the most promising ideas is called antimatter propulsion, and it would be the ultimate expression of Einstein's famous equation E=mc². Antimatter is exactly what it sounds like. It's matter with opposite properties to normal matter. When antimatter comes into contact with regular matter, both particles are completely annihilated and converted directly into pure energy. This isn't like fusion, where a tiny fraction of matter becomes energy. With antimatter, the entire mass of both particles becomes energy according to Einstein's equation. It's the most efficient energy conversion possible in the universe. A spacecraft powered by antimatter could theoretically reach speeds of 50% or even 70% of light speed. At those velocities, time dilation effects from Einstein's relativity would actually help the crew. A journey that takes 10 years from Earth's perspective might only feel like 6 or 7 years to the people on the spacecraft. Suddenly, interstellar travel becomes not just possible, but practical for human crews. The energy density of antimatter is almost impossible to comprehend. A single gram of antimatter re-gram of regular acting with a matter would release the same amount of energy as exploding 43,000 tons of TNT. That's roughly 3 times the power of the atomic bomb dropped on Hiroshima from just 2 grams of material. A spacecraft carrying a few pounds of antimatter would have more energy available than all the chemical rockets ever built combined. Scientists at CERN and other particle physics laboratories have successfully created antimatter in tiny quantities. We're talking about individual atoms, not grams or pounds. But the fact that we can create it at all proves that antimatter propulsion isn't just theoretical. The technology exists, even if it's still incredibly primitive. The challenges with antimatter are staggering though. First, creating antimatter requires enormous amounts of energy. Current methods are so inefficient that it takes billions of times more energy to create antimatter than you get back when it annihilates. Second, storing antimatter is incredibly difficult because it destroys any normal matter it touches. Scientists have to use magnetic fields to trap antimatter particles in perfect vacuums, and even then, the storage systems are complex and fragile. But here's what's encouraging. Every single one of these problems is an engineering challenge, not a fundamental physics limitation. We know antimatter works. We know it can be created and stored. We know the physics of antimatter propulsion. What we need is better technology and more efficient production methods. Some scientists believe that advances in particle physics and magnetic confinement could make antimatter propulsion practical within 100 years. That might sound like a long time, but remember that powered flight went from the Wright brothers to landing on the moon in just 66 years. Technological development can accelerate rapidly when there's sufficient motivation and resources. There's also a wildcard technology that could change everything overnight. It's called breakthrough propulsion physics, and it involves concepts that sound like pure-edge theoretical science fiction but are based on cutting physics. Ideas like manipulating space-time itself, creating artificial gravity fields, or even finding ways to travel faster than light without actually violating Einstein's speed limit. One of the most intriguing concepts is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The idea is to contract space in front of a spacecraft and expand space behind it, creating a bubble of warped space-time that could theoretically travel faster than light, while the spacecraft inside remains stationary relative to its local space. It's like moving the space around the ship instead of moving the ship through space. The mathematics of the Alcubierre drive are consistent with Einstein's general relativity. There's no violation of physics involved, but the engineering requirements are beyond anything we can currently imagine. Creating the necessary space-time distortion would require exotic matter with negative energy density, something that may not even exist in nature. Recent research has suggested that the energy requirements for an Alcubierre drive might be reducible through clever engineering. Some physicists believe that instead of requiring the mass energy of Jupiter, an optimized warp drive might only need the equivalent of a few tons of matter converted to pure energy. That's still an enormous amount of energy, but it's not impossible. NASA's Advanced Propulsion Physics Laboratory, informally known as the Eagle Works Lab, has been quietly researching these exotic propulsion concepts for years. They've investigated everything from electromagnetic drives to quantum vacuum fluctuations. Most of their experiments haven't produced practical results, but they've advanced our understanding of the fundamental physics involved. The reality is that we're probably decades away from any breakthrough propulsion technology that could enable faster-than-light travel. But the theoretical foundations are being laid right now by physicists and engineers who are pushing the boundaries of what we think is possible. What's absolutely certain is that our species will not remain confined to this solar system forever. The combination of advancing technology, human curiosity, and the fundamental drive to explore and expand makes interstellar travel inevitable. The only real question is which technology will get us there first and how long it will take. The most likely scenario is that we'll see multiple approaches developing simultaneously. Robotic light sail probes could reach nearby stars within the next few decades, providing our first detailed look at exoplanets and potentially habitable worlds. Fusion-powered spacecraft might follow in the latter half of this century, carrying more sophisticated scientific equipment and perhaps even small human crews on one-way colonization missions. Meanwhile, research into more exotic propulsion methods will continue in laboratories around the world. Breakthrough discoveries in physics or engineering could suddenly accelerate our timeline for interstellar travel. History shows that technological development rarely follows predictable paths. Sometimes decades of slow progress are followed by sudden leaps that transform entire civilizations. But here's something most people don't realize about our quest to escape the solar system. We're not starting from scratch. Right now, at this very moment, there are 5 human-made objects that have already broken free from our sun's gravitational prison. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons have all crossed into interstellar space, becoming humanity's first ambassadors to the galaxy beyond. These spacecraft weren't designed for interstellar travel. They were built in the 1970s and 2000s, using technology that's ancient by today's standards. Yet they've given us invaluable insights into what it actually takes to leave our cosmic neighborhood and what we might encounter out there in the vast emptiness between stars. Voyager 1 crossed the boundary into interstellar space in 2012, after 35 years of travel. The moment it happened, scientists around the world knew they were witnessing history. For the first time ever, we had a human-made object sending back data from beyond our solar system, and what it found was both fascinating and terrifying. The space between stars isn't empty like we thought. It's filled with charged particles, magnetic fields, and radiation that's far more intense than anything we experience in our protected bubble around the sun. The interstellar medium, as scientists call it, is like a cosmic ocean with currents and storms that could destroy unprotected spacecraft. Understanding these conditions is crucial for designing future interstellar missions. What's even more remarkable is that these ancient spacecraft are still talking to us, despite being billions of miles away, running on less power than a refrigerator light bulb, and using 1970s computer technology that's millions of times less powerful than your smartphone. They continue transmitting data back to Earth. The engineering that went into making these missions last decades longer than originally planned teaches us valuable lessons about building spacecraft for the ultimate long-distance journey. But the Voyager missions also revealed just how unprepared we were for true interstellar exploration. These spacecraft are essentially flying blind through interstellar space. They have no ability to navigate, no way to avoid obstacles, and no means of self-repair. They're gradually dying as their power sources decay and their instruments fail one by one. Within the next decade, we'll lose contact with them forever, leaving us once again isolated within our solar system. This is why the next generation of interstellar spacecraft needs to be fundamentally different. We can't just build bigger versions of Voyager. We need spacecraft that can think for themselves, repair themselves, and adapt to conditions we can't predict from Earth. Artificial intelligence isn't just helpful for interstellar missions, it's absolutely essential. Consider the communication challenge alone. Radio signals travel at the speed of light, which sounds fast until you're dealing with interstellar distances. A message from a spacecraft at Proxima Centauri would take 4.2 years to reach Earth, and our response would take another 4.2 years to get back. That's an 8.4-year delay for a simple question and answer. By the time mission controllers on Earth realize there's a problem, the spacecraft could have been destroyed for years. This means interstellar spacecraft must be autonomous in ways that no previous space mission has ever required. They need to make split-second decisions about navigation, conduct their own scientific observations, and even modify their mission objectives based on what they discover. We're not just talking about remote-controlled robots. We're talking about truly intelligent explorers that can think and learn independently. The good news is that artificial intelligence technology is advancing at an incredible pace. Machine learning systems can already recognize patterns, make predictions, and solve problems that would have been impossible for computers just a few years ago. By the time we're ready to launch serious interstellar missions, AI systems will likely be sophisticated enough to serve as the brains of autonomous interstellar explorers. But intelligence isn't enough. These spacecraft also need to survive in an environment that's actively hostile to technology. Cosmic radiation in interstellar space is intense enough to gradually destroy electronic components. Microscopic dust particles traveling at high speeds can punch holes through spacecraft like bullets, and the extreme cold of space, just a few degrees above absolute zero, creates thermal stresses that can crack materials and cause systems to fail. This is driving the development of self-repairing spacecraft technology. Scientists are working on materials that can heal themselves when damaged, electronic systems that can reroute around failed components, and even 3D printing capabilities that would allow spacecraft to manufacture replacement parts during the journey. Some concepts involve spacecraft that could literally rebuild themselves using raw materials they encounter in space. The most ambitious ideas involve what scientists call von Neumann probes, named after mathematician John von Neumann, who first described self-replicating machines. These would be spacecraft capable of not just repairing themselves, but actually building copies of themselves using materials they find in space. A single von Neumann probe could potentially explore an entire galaxy by creating thousands or millions of copies of itself. The implications are staggering. Instead of sending one expensive spacecraft to one star system, we could send a single self-replicating probe that would eventually explore hundreds or thousands of star systems simultaneously. Each copy would send back data about different worlds, different conditions, different possibilities for life or resources or colonization. Of course, self-replicating spacecraft also raise some serious concerns. What happens if the replication process goes wrong and creates defective copies? What if the spacecraft evolve beyond our control and develop their own agendas? Science fiction has explored these scenarios extensively, but they're becoming real engineering considerations as we develop increasingly sophisticated autonomous systems. The timeline for deploying truly advanced interstellar spacecraft is still measured in decades, but the foundational technologies are being developed right now. NASA's Artemis program isn't just about returning to the moon. It's about testing life support systems, radiation shielding, and autonomous navigation that will eventually be needed for interstellar missions. The Mars exploration program is teaching us how to operate robotic systems across interplanetary distances, which is essential preparation for interstellar operations. Private companies are also pushing the boundaries of what's possible. SpaceX has revolutionized launch costs and spacecraft reusability. Blue Origin is developing technologies for long-duration space travel. Breakthrough Starshot continues advancing light sail technology. The combination of government research and private innovation is accelerating progress in ways that wouldn't have been possible with traditional space program approaches alone. But perhaps the most important development isn't technological at all, it's psychological and cultural. For the first time in human history, escaping our solar system has moved from pure science fiction into serious scientific and engineering planning. Universities offer courses in interstellar mission design. International conferences bring together researchers working on breakthrough propulsion. Government agencies allocate budgets for studying technologies that seemed impossible just decades ago. This shift in perspective matters because interstellar travel isn't just a technical challenge. It's a civilizational project that will require sustained effort across multiple generations. The spacecraft we launch in the 2040s might not reach their destinations until the 2060s or later. The people who design these missions might not live to see the results. This requires a long-term vision and commitment that goes far beyond typical technology development cycles. Yet signs that humanity there is ready for this challenge. The international cooperation we've seen on projects like the International Space Station and the James Webb Space Telescope demonstrates that we can work together on ambitious long-term scientific endeavors. The growing private space industry shows that interstellar exploration isn't dependent on government funding alone, and the increasing public interest in space exploration, driven partly by private missions and space tourism, suggests that society is ready to support more ambitious projects. The economic incentives are also becoming clearer. While the first interstellar missions will be purely scientific, future missions could have enormous economic value. Asteroid mining within our solar system could provide vast mineral wealth. The resources available in other star systems dwarf anything we could access locally. A single metallic asteroid in another star system might contain more platinum than exists on all of Earth. Even more valuable could be the discovery of habitable worlds or existing life forms. The scientific and technological knowledge gained from studying alien ecosystems or alien technology could revolutionize human civilization in ways we can barely imagine. The economic return on investment for successful interstellar exploration could be measured not in billions or trillions of dollars, but in the transformation of human society itself. This is why some economists argue that interstellar exploration isn't just an expense, but potentially the most profitable investment humanity could make. The challenge is that the investment happens today, while the returns might not materialize for decades or centuries. It requires the kind of long-term thinking that's often difficult in societies focused on quarterly profits and election cycles. But history shows that transformative technologies often develop faster than experts predict. The internet went from a military research project to a global communication system in just a few decades. Smartphones went from science fiction to ubiquitous technology in less than 20 years. Artificial intelligence has progressed from simple pattern recognition to systems that can write, create art, and solve complex problems in just the last few years. The same kind of exponential progress could happen with interstellar travel technology. A breakthrough in fusion propulsion, antimatter storage, or exotic physics could suddenly make interstellar missions practical decades earlier than current projections suggest. This is why research into multiple approaches simultaneously is so important. We can't predict which technology will provide the breakthrough, so we need to pursue all promising avenues. There's also the possibility that we'll discover something completely unexpected that changes everything. Every major advance in physics has revealed new phenomena that previous generations couldn't have imagined. Quantum mechanics gave us lasers, computers, and MRI machines. Relativity led to GPS satellites and nuclear power. What will the next major physics breakthrough enable? Some physicists believe we're on the verge of discoveries that could revolutionize our understanding of space, time, and energy. Research into dark matter and dark energy, which make up 95% of the universe but remain mysterious, could reveal new forms of propulsion. Studies of quantum entanglement might lead to faster-than-light communication systems. Investigation of the quantum vacuum could unlock energy sources that make antimatter look primitive. The point is that we're living through a period of unprecedented scientific and technological advancement. The tools we're developing to explore our solar system are the same tools that will eventually take us to the stars. Every Mars rover, every deep space telescope, every breakthrough in materials science or artificial intelligence brings us one step closer to becoming an interstellar civilization. And we're not just preparing the technology, we're preparing ourselves. Astronauts on the International Space Station are learning how to live and work in space for extended periods. Researchers in Antarctica and other isolated locations are studying the psychological challenges of long-duration missions with limited contact with home. Advances in medicine and life support systems are extending the human ability to survive in hostile environments. Perhaps most importantly, we're developing the cultural and philosophical frameworks we'll need to be an interstellar species. Questions about how to govern multi-generational missions, how to preserve human culture across interstellar distances, and how to make decisions that affect people who won't be born for decades are being discussed seriously for the first time. The truth is that escaping our solar system isn't just about building faster spaceships or more powerful rockets. It's about fundamentally changing what it means to be human. It's about expanding our species beyond the single planet that gave birth to us, beyond the single star system that has been our entire universe for all of human history. We're closer to this transformation than most people realize. The technologies exist or are being developed. The scientific understanding is advancing rapidly. The economic and political will is building. And most importantly, the vision of humanity as an interstellar civilization is taking hold in ways that would have been unimaginable just a generation ago. The solar system that has been our home for millions of years of evolution might soon become just our starting point. The cosmic prison that has confined every human who has ever lived is about to become an open door to unlimited possibilities among the stars. The question isn't whether we'll escape our solar system anymore. The question is which method will get us there first, and the answer might surprise you because the most promising approach isn't the one getting the most attention. While fusion rockets and antimatter drives capture headlines with their incredible potential speeds, there's a quieter revolution happening in propulsion physics that could leapfrog all of these technologies. It's called nuclear pulse propulsion, and it's based on a concept so simple yet so powerful that it was actually tested successfully in the 1960s before being abandoned for political reasons. The idea behind nuclear pulse propulsion is elegantly straightforward. Instead of trying to contain nuclear reactions inside an engine, you detonate small nuclear devices behind your spacecraft and ride the shock waves. Each explosion pushes against a massive steel plate called a pust to the crew plate, which is connected compartment through an elaborate shock absorption system. It's like propelling a canoe by throwing hand grenades into the water behind you, except the physics actually work beautifully at the scale of spacecraft. The original project was called Orion, and it was developed by some of the brightest minds in nuclear physics and aerospace engineering. They built working prototypes using conventional explosives that successfully demonstrated the concept. The test vehicles reached altitudes of several hundred feet, powered entirely by controlled explosions, proving that pulse propulsion could work in practice, not just on paper. What made Orion so revolutionary was its performance potential. The calculations showed that a nuclear pulse spacecraft could reach speeds of up to 5% of light speed, making trips to nearby stars possible in less than a century. More importantly, these weren't theoretical projections based on unproven physics. They were engineering estimates based on nuclear weapons technology that already existed. The Orion project was cancelled in 1965, not because of technical problems, but because of the Nuclear Test Ban Treaty, which prohibited nuclear explosions in space. The engineers had solved the major technical challenges and were ready to build full-scale spacecraft when political considerations shut down the program. For decades, nuclear pulse propulsion seemed like a dead end, a fascinating might-have-been in the history of space exploration. But that's changing rapidly. New international treaties specifically allow nuclear propulsion for peaceful space exploration, and advances in nuclear technology have made pulse propulsion far more practical than it was in the 1960s. Modern computer simulations can optimize explosion timing and spacecraft design with precision that wasn't possible with 1960s technology. Advanced materials can handle the thermal and mechanical stresses much better than the steel and aluminum available to the original Orion team. More importantly, we now have miniaturized nuclear devices specifically designed for propulsion rather than weapons. These shaped charges can direct their energy more efficiently, reducing the size of explosions needed while increasing the thrust delivered to the spacecraft. Some designs use fusion pellets no larger than aspirin tablets, each containing enough energy to accelerate a multi-ton spacecraft by several meters per second. The engineering 90s are becoming challenges that seemed insurmountable in the first manageable with 21st century technology. The shock absorption systems that protect the crew from the violence of nuclear explosions can now be designed using advanced computer modeling and built with materials that didn't exist decades ago. The timing systems that coordinate thousands of precisely timed detonations can use GPS-accurate atomic clocks and quantum sensors, but nuclear pulse propulsion has one overwhelming advantage that makes it especially attractive for interstellar missions. Unlike ion drives that take months to build up speed, or fusion rockets that require exotic fuel handling systems, pulse propulsion can achieve enormous velocities relatively quickly using technology we already understand. A nuclear pulse spacecraft could accelerate to interstellar cruise speeds within days or weeks of leaving Earth orbit. This rapid acceleration solves several practical problems that plague other interstellar propulsion concepts. The crew spends less time exposed to cosmic radiation because they reach their destination faster. The mission requires less life support consumables because the journey is shorter. Most importantly, the people who design and launch the mission have a realistic chance of living to see the results. Russian scientists have been quietly developing their own version of nuclear pulse propulsion called the nuclear pulse engine. Their approach uses smaller, more frequent explosions rather than the large charges envisioned by the original Orion project. Computer simulations suggest this could provide smoother acceleration while achieving similar performance, making it more suitable for crewed missions. The Chinese space program has also expressed interest in nuclear pulse technology, though their research remains largely classified. What we do know is that they've been testing nuclear thermal rockets, which use nuclear reactors to heat propellant rather than nuclear explosions for thrust. This suggests they're seriously investigating all forms of nuclear propulsion as part of their long-term space exploration strategy. But here's what makes nuclear pulse propulsion truly revolutionary for interstellar travel. The technology scales incredibly well. A small probe using pulse propulsion might reach 3% of light speed, making the journey to Proxima Centauri in about 140 years. But a larger spacecraft with more powerful charges could potentially reach 8% or even 10% of light speed, cutting that journey time to 40 or 50 years. At those speeds, we're talking about missions that could be completed within a human lifetime. Scientists who design and launch an interstellar mission in their 30s could still be alive to analyze the data when it returns. That changes everything about how we approach interstellar exploration, because it transforms these missions from multi-generational commitments into ambitious but achievable single-lifetime projects. The psychological impact of achievable timelines cannot be overstated. It's one thing to fund a mission that might produce results in 200 years. It's entirely different to support a mission that will definitely produce results in your own lifetime or your children's lifetime. Nuclear pulse propulsion could make interstellar exploration politically and economically viable in ways that longer duration missions never could be. Recent advances in nuclear weapons technology have also made pulse propulsion safer and more controllable. Modern nuclear devices can be designed with incredibly precise energy outputs and shaped charges that direct their force exactly where needed. The explosions can be timed to microsecond precision, allowing for smooth acceleration profiles that would be comfortable for human crews. Safety systems that seemed impossible in the 1960s are now routine in nuclear facilities around the world. Remote handling systems can manage nuclear materials without human exposure to radiation. Automated safety systems can shut down propulsion systems faster than human operators could react. Computer modeling can predict and prevent failure modes that earlier generations of engineers couldn't even identify. But perhaps most importantly, we now have decades of experience operating nuclear reactors in space. Soviet and American spacecraft have used nuclear power sources for decades without major incidents. The engineering challenges of nuclear pulse propulsion are significant, but they're not unprecedented in the context of space nuclear systems we've already built and operated successfully. The timeline for nuclear pulse propulsion development is remarkably aggressive compared to other interstellar technologies. Because the basic physics are well understood and the nuclear technology already exists, engineers estimate that a working prototype could be built within 15 years if adequate funding were available. A full-scale interstellar mission could launch by the 2050s, with arrival at nearby stars in the 2090s. That's not science fiction, that's engineering projection based on existing technology and reasonable development timelines. We could see the first detailed exploration of another star system within the lifetime of people alive today. The images and data from that mission would transform our understanding of planetary formation, the possibility of life beyond Earth, and our place in the cosmic order. But nuclear pulse propulsion isn't the only game-changing technology that's closer to reality than most people think. There's another approach that could potentially get us to nearby stars even faster, and it's based on physics so exotic that it sounds like magic even to scientists who work with it every day. It's called quantum propulsion, and it exploits one of the strangest phenomena in quantum mechanics. At the smallest scales, the seemingly empty vacuum of space is actually filled with virtual particles that constantly pop into existence and disappear again. This quantum foam contains enormous amounts of energy, but it's normally impossible to access because the virtual particles cancel each other out almost instantly. Recent experiments have shown that under certain conditions, it might be possible to create what physicists call a quantum vacuum thruster. By manipulating the quantum vacuum with precisely controlled electromagnetic fields, a spacecraft could potentially extract energy directly from empty space itself. The physics are still being worked out, but the experimental evidence suggests that quantum vacuum effects are real and potentially exploitable. NASA's Eagle Works laboratory has been quietly investigating quantum vacuum propulsion for several years. Their experiments have produced thrust measurements that are small but consistent, suggesting that some kind of quantum vacuum interaction is actually occurring. While the forces are currently tiny, the theoretical potential is staggering because the energy source is essentially unlimited. A spacecraft powered by quantum vacuum extraction wouldn't need to carry fuel at all. It would draw energy directly from the structure of space-time itself, potentially allowing for continuous acceleration limited only by the engineering constraints of the propulsion system. Such a spacecraft could theoretically reach significant fractions of light speed while carrying substantial payloads, making it ideal for both robotic exploration and eventual human colonization missions. The engineering challenges are formidable because quantum vacuum effects operate at scales where the normal rules of engineering don't apply, creating the precisely controlled electromagnetic fields needed to manipulate virtual particles requires technology that's barely possible with current superconducting systems. Scaling up from laboratory demonstrations to spacecraft-sized systems presents problems that may take decades to solve. But the potential payoff is so enormous that multiple research groups around the world are working on quantum vacuum propulsion. Chinese scientists have published papers describing their own experimental results. European researchers are investigating related phenomena in particle accelerators. The field is advancing rapidly as our understanding of quantum mechanics becomes more sophisticated. What makes quantum vacuum propulsion especially intriguing is that it could potentially enable not just fast interstellar travel, but faster-than-light communication. If spacecraft can manipulate quantum vacuum fields, they might be able to create quantum entanglement effects that allow instantaneous information transfer across arbitrary distances. That would solve the communication delay problem that plagues conventional interstellar missions. Imagine launching a quantum vacuum-powered spacecraft to Proxima Centauri that maintains real-time communication with Earth throughout its journey. Mission controllers could guide the exploration in real time, making discoveries and adjusting plans as the mission unfolds rather than waiting years for each communication cycle. The scientific return from such missions would be orders of magnitude greater than anything possible with conventional propulsion and communication systems. The timeline for practical quantum vacuum propulsion is much more uncertain than nuclear pulse propulsion because we're still working out the basic physics. Current experiments produce thrust levels measured in micronewtons, which is millions of times smaller than what would be needed for spacecraft propulsion. But if the theoretical predictions are correct, scaling up might be possible through engineering advances rather than new physics discoveries. Some physicists believe we could see working quantum vacuum thrusters within 20 to 30 years. Others think it might take 50 years or more to develop practical systems. The uncertainty reflects how revolutionary this technology would be. We're not just talking about a better rocket engine, we're talking about a propulsion system that operates on fundamentally different principles than anything humans have ever built. But here's the really exciting part about our current moment in history. We don't have to choose between these different approaches. Multiple technologies are advancing simultaneously, each with different advantages and development timelines. We could see nuclear pulse propulsion reaching nearby stars in the 2090s, while quantum vacuum systems are still being developed. Or quantum breakthroughs could leap ahead of nuclear pulse technology, getting us to the stars decades earlier than current projections suggest. The diversity of approaches actually increases our chances of success because different technologies might be optimal for different types of missions. Light sail probes might be best for initial reconnaissance of nearby star systems. Nuclear pulse spacecraft could carry larger scientific payloads and eventually human crews. Quantum vacuum systems might enable the permanent human colonization of other star systems by providing unlimited energy for life support and manufacturing. What's certain is that the next few decades will see unprecedented advances in propulsion physics and spacecraft engineering. The combination of government research, private investment, and international cooperation is creating a perfect storm of innovation that's accelerating progress in ways that wouldn't have been possible in previous generations. Private companies are already investing billions of dollars in advanced propulsion research. Government agencies are funding increasingly ambitious projects. Universities are producing graduates with expertise in exotic propulsion concepts that were pure theory just a few years ago. The entire field is gaining momentum and resources at an exponential rate. But the most important factor driving progress toward interstellar travel isn't technological. It's the growing recognition that escaping our solar system isn't just an interesting scientific challenge, but an essential requirement for the long-term survival of human civilization. Earth faces multiple existential risks, from asteroid impacts to supervolcanic eruptions to the gradual brightening of our sun as it ages. Becoming an interstellar species isn't just about exploration and discovery. It's about ensuring that human consciousness and culture can survive cosmic catastrophes that would destroy any single-planet civilization. This existential motivation is transforming how we think about interstellar travel. It's no longer a distant dream for future generations to pursue when they have nothing better to do. It's becoming an urgent priority for our generation to begin seriously, with the understanding that the work we do today will determine whether humanity has a future beyond our solar system. The technologies we've discussed aren't just interesting physics experiments. They're the tools that could transform us from a planetary species confined to one star system into a galactic civilization spread across multiple worlds orbiting different stars. The decisions we make about funding, research priorities, and international cooperation over the next few decades will determine how quickly that transformation occurs. And it will occur. The physics are sound. The engineering challenges are solvable, and the motivation is becoming undeniable. The only real question is whether it happens in our lifetime or our children's lifetime or our grandchildren's lifetime. The answer depends on how seriously we take this challenge and how much effort we're willing to invest in becoming an interstellar species. The cosmic prison that has held us for all of human history is about to become an open door. The question isn't whether we'll walk through it. The question is how fast we'll run toward the stars that are waiting for us in the vast darkness beyond our solar system's edge. The engineering timeline for these breakthrough technologies is accelerating faster than most experts predicted just 5 years ago. What seemed like century-long development cycles are being compressed into decades through advances in computer modeling, materials science, and manufacturing techniques. We're witnessing the same kind of exponential progress that transformed the computer industry, except now it's happening with spacecraft propulsion systems that could carry us to other worlds. Consider how rapidly our understanding of nuclear pulse propulsion has evolved. In 2019, most physicists considered it an interesting historical footnote, a Cold War project that died with the test ban treaties. Today, multiple nations have active research programs developing modernized versions that solve the safety and efficiency problems that plagued the original Orion design. The theoretical performance hasn't changed, but the engineering solutions have become dramatically more sophisticated. Modern nuclear pulse systems use shaped charges smaller than golf balls, each precisely engineered to direct their energy through magnetic fields that focus the blast into thrust vectors. Computer simulations can now model the interaction between thousands of these micro-explosions and the spacecraft structure with accuracy that would have required years of physical testing in the 1960s. We can design shock absorption systems that protect human crews while maximizing energy transfer efficiency. But there's something even more remarkable happening in propulsion physics that most people haven't heard about yet. It's called field manipulation propulsion, and it's based on discoveries in electromagnetic field theory that were only confirmed experimentally in the last decade. The basic principle involves creating asymmetric electromagnetic fields that interact with the quantum vacuum in ways that produce net thrust without expelling mass. This isn't the same as the electromagnetic drives that generated controversy a few years ago. Those systems violated conservation of momentum and were ultimately debunked. Field manipulation propulsion works within known physics by exploiting the fact that electromagnetic fields carry momentum and can transfer that momentum to spacecraft through carefully designed field geometries. The thrust levels achieved so far are microscopic, measured in thousandths of a newton, but the significance isn't in the current performance, it's in the proof of concept. For the first time, we've demonstrated that spacecraft can generate thrust by manipulating electromagnetic fields rather than by throwing mass overboard. The implications for interstellar travel are staggering because such systems could operate indefinitely without fuel constraints. Research groups in Japan, Germany, and the United States have independently verified the basic effect. The engineering challenge now is scaling up from laboratory demonstrations to systems powerful enough for spacecraft propulsion. Some researchers believe this could happen within 15 years, others think it might take 30 years. But everyone agrees that the physics work, which makes field manipulation propulsion a legitimate candidate for interstellar missions. What makes this technology especially promising is its potential for hybrid systems that combine multiple propulsion methods. A spacecraft could use chemical rockets for initial acceleration out of Earth's gravity well, switch to ion drives for efficient cruising through the solar system, then activate field manipulation systems for the final push to interstellar speeds. Each technology would operate in the regime where it's most effective, maximizing overall mission performance. The hybrid approach also provides redundancy that's crucial for missions lasting decades or centuries. If one propulsion system fails, the spacecraft could still complete its mission using backup systems. This kind of fault tolerance is essential for interstellar missions because repair and resupply from Earth will be impossible once the spacecraft leaves our solar system. But perhaps the most exciting development in interstellar propulsion isn't any single technology. It's the convergence of artificial intelligence, advanced materials, and miniaturized manufacturing that's making self-modifying spacecraft possible. These aren't just robots that follow pre-programmed instructions. They're systems that can redesign and rebuild themselves during flight, optimizing performance for rising their conditions they encounter in interstellar space. Imagine a spacecraft that begins its journey using conventional ion propulsion, but gradually converts itself into a light sail as it moves farther from the sun, and solar radiation becomes less useful for power generation. Or a probe that starts as a single large vehicle but splits into dozens of smaller specialized units as it approaches its target star system, each optimized for different types of scientific observation. The technology for this kind of adaptive spacecraft is being developed right now in laboratories around the world. 3D printing systems can already manufacture electronic components, structural materials, and even simple machines from raw feedstock. Artificial intelligence systems can design optimized structures and circuits for specific performance requirements. Self-assembling materials can reorganize themselves into new configurations when triggered by environmental conditions. Combining these technologies creates spacecraft that aren't just tools for exploration, but intelligent agents capable of evolving and adapting throughout their missions. Such systems could potentially repair themselves when damaged by cosmic radiation or micrometeorite impacts. They could reconfigure themselves to take advantage of unexpected opportunities, like using gravitational assists from previously unknown objects or harvesting materials from asteroids they encounter along the way. The timeline for self-modifying spacecraft is remarkably aggressive because all the component technologies already exist in primitive forms. NASA's Artemis program is testing 3D printing systems for manufacturing tools and spare parts on the lunar surface. Private companies are developing AI systems that can optimize spacecraft trajectories and resource allocation in real time. Materials scientists are creating smart materials that can change their properties in response to environmental triggers. Integrating these technologies into functional interstellar spacecraft is primarily an engineering challenge rather than a fundamental research problem. Multiple aerospace companies are working on demonstration missions that could launch within the next decade, testing self-modification capabilities in Earth orbit before committing to interstellar missions. What's remarkable is how these different approaches to interstellar travel are all advancing simultaneously, creating multiple possible paths to the stars. We don't have to wait for any single breakthrough technology to mature. Instead, we're developing a toolkit of propulsion methods, navigation systems, and spacecraft architectures that can be combined in different ways depending on mission requirements and technological readiness. The first interstellar missions will probably use the technologies that are closest to operational readiness, which currently appear to be light sail systems for small robotic probes. But the spacecraft that follow could use completely different approaches as more advanced technologies become available. We might see nuclear pulse ships launching while quantum vacuum systems are still being developed, or self-modifying spacecraft that start with propulsion method and evolve to use others during their journey. This technological diversity actually increases our chances of success because different approaches, different risk have profiles and development timelines. If one technology encounters unexpected problems, others can continue advancing. If breakthrough discoveries accelerate one approach, it can leap ahead of alternatives that seemed more promising just years earlier. The history of aviation provides a perfect analogy. The Wright brothers achieved powered flight using internal combustion engines, but within decades, aircraft were using jet engines, rocket engines, and even nuclear power plants. Each technology found its optimal application based on mission requirements and performance characteristics. The same thing will happen with interstellar propulsion as different technologies mature and find their ideal roles. But there's an even deeper transformation happening that goes beyond propulsion technology. We're fundamentally changing how we think about space missions themselves. Traditional spacecraft are designed, built, launched, and operated according to fixed parameters established before launch. Interstellar missions will need to be adaptive, evolutionary, and autonomous in ways that no previous space mission has required. This shift toward intelligent, adaptive spacecraft is being driven by the unique challenges of interstellar distances and timescales. Communication delays measured in years make real-time mission control impossible. Journey times measured in decades or centuries exceed human attention spans and institutional memory. Environmental conditions in interstellar space remain largely unknown, making detailed pre-mission planning impossible. The solution is spacecraft that can think, learn, and evolve independently. These systems need to make complex decisions about navigation, resource allocation, and mission objectives without human guidance. They need to adapt to conditions that weren't anticipated during mission design. Most importantly, they need to maintain and improve themselves throughout journeys that could last longer than human civilizations. Recent advances in machine learning and artificial intelligence are making this kind of autonomous operation increasingly realistic. AI systems can already optimize complex systems in real time, learn from experience, and even discover new solutions to problems they weren't explicitly programmed to solve. Scaling these capabilities up to interstellar mission requirements is challenging, but it's clearly within the realm of possibility. The psychological and cultural implications of truly autonomous interstellar missions are as significant as the technical challenges. These spacecraft will be humanity's first completely independent ambassadors to other star systems. They'll make first contact with alien life forms, if such life exists, without human oversight or guidance. They'll represent human civilization to the galaxy, making decisions that could affect our species' reputation among any intelligent beings they encounter. This responsibility requires building ethical frameworks and decision-making capabilities into interstellar spacecraft that go far beyond simple mission parameters. These systems need to understand human values, cultural principles, and long-term interests in ways that allow them to make appropriate choices in situations we can't anticipate. They need to be not just intelligent, but wise. The development of such sophisticated autonomous systems is happening faster than most people realize. Military applications are driving advances in AI systems that can operate independently in complex, hostile environments. Commercial applications are creating AI systems that can manage resources, optimize performance, and adapt to changing conditions without human intervention. Space applications are testing AI systems that can navigate, communicate, and conduct scientific research with minimal human oversight. Combining these advances with the propulsion technologies we've discussed creates a complete picture of how interstellar missions will actually work. Intelligent, adaptive spacecraft powered by advanced propulsion systems will launch toward nearby star systems within the next few decades. These missions will be humanity's first serious attempts to escape our cosmic prison and explore the galaxy beyond our solar system. The timeline is becoming increasingly clear as technologies mature and converge. Light sail probes could launch toward Proxima Centauri within the next 10 to 15 years, reaching their destination around 2050. Nuclear pulse missions could follow in the 2040s or 2050s, carrying more sophisticated scientific equipment and arrivings or 2090s. More at nearby stars in the 2080 Eorzean systems, like advanced prop quantum vacuum drives or field manipulation systems, could enable even faster missions if breakthrough discoveries accelerate their development. What this means is that people alive today will likely witness the first detailed exploration of other star systems. The images, data, and discoveries from these missions will transform our understanding of planetary formation, the prevalence of life in the universe, and our place in the cosmic order. We're living at the moment when humanity transitions from a single-planet species to an interstellar civilization. The engineering challenges are enormous, but they're not insurmountable. The physics are well understood, even if the engineering solutions are still being developed. The technologies exist in various stages of maturity, with multiple approaches advancing simultaneously. Most importantly, the recognition that interstellar travel is both possible and necessary is driving unprecedented investment in research and development. What's particularly encouraging is how rapidly progress is accelerating. Advances in computer modeling, materials science, manufacturing techniques, and artificial intelligence are solving problems that seemed intractable just a few years ago. The same exponential progress that transformed computing, telecommunications, and biotechnology is now being applied to spacecraft propulsion and interstellar mission design. Private companies are investing billions of dollars in advanced propulsion research because they recognize the enormous commercial potential of interstellar capabilities. Government agencies are funding increasingly ambitious projects because they understand the strategic importance of space-based resources and technologies. Universities are producing graduates with expertise in exotic physics and advanced engineering because these fields are becoming essential for future economic and technological development. International cooperation is also accelerating progress in ways that wouldn't have been possible during previous eras of space exploration. The challenges of interstellar travel are so enormous that no single nation can address them independently, Pooling resources, expertise, and funding across multiple countries creates synergies that accelerate technological development while reducing costs and risks for individual participants. The result is a perfect storm of technological advancement, economic investment, and international cooperation that's making interstellar travel not just possible, but inevitable. The question isn't whether humanity will escape our solar system. The question is how quickly we'll make the transition and which technologies will prove most effective for different types of missions. Current projections suggest we'll see the first successful interstellar missions within the next 30 years, with increasingly sophisticated missions following as technologies mature and improve. By the end of this century, interstellar travel could become routine, with multiple missions launching toward different star systems every few years. The transformation from a single planet species to an interstellar civilization will happen gradually at first, then accelerate rapidly as technologies mature and missions prove successful. The first interstellar probes will be small, simple, and limited in their capabilities, but they'll pave the way for larger, more sophisticated missions that can carry advanced scientific equipment and eventually human crews. Within a century or two, we could see permanent human settlements established around other stars, connected to Earth and each other through a network of interstellar transportation and communication systems. Humanity will have broken free from our cosmic prison and spread throughout the galaxy, ensuring our species' survival regardless of what catastrophes might befall our home planet. The technologies that will make this transformation possible are being developed right now in laboratories, universities, and companies around the world. The basic physics are understood, the engineering challenges are being solved, and the timeline for practical interstellar travel is becoming increasingly realistic. We're living at one of the most significant moments in human history when our species is taking its first serious steps toward becoming an interstellar civilization. The cosmic prison that has confined us for millions of years of evolution is about to become an open door to unlimited possibilities among the stars. The only question remaining is how quickly we'll have the courage to walk through that door and claim our destiny in the galaxy beyond. The escape velocity we need isn't just about speed, though. It's about sustaining that speed across distances that make our solar system look microscopic. Think about this for a moment. The fastest human-made object ever created, the Parker Solar Probe, achieved 430,000 miles per hour by falling toward the Sun. That's incredibly fast by any earthly standard. You could travel from New York to Los Angeles in about 90 seconds at that speed. But even at that breakneck velocity, it would still take over 6,000 years to reach the nearest star. This is where the true genius of modern propulsion concepts reveals itself. We're not trying to build faster versions of existing rockets. We're developing entirely new ways to think about movement through space itself. And some of these approaches are so counterintuitive that they seem to violate common sense, even when the physics are perfectly sound. Take the concept of breakthrough propulsion physics that NASA's been quietly investigating for over 2 decades. They're not just looking at better engines, they're examining whether we can manipulate the fundamental structure of space-time itself. The Alcubierre drive isn't science fiction anymore. It's a legitimate area of research with real funding and serious scientists working on the mathematics. The latest calculations suggest that creating a warp bubble might not require the mass energy equivalent of Jupiter, like originally thought. New models indicate we might be able to achieve space-time distortion with energy levels comparable to what we already use for particle accelerators. That's still an enormous amount of energy, but it's within the realm of advanced engineering rather than impossible physics. But here's what makes this research particularly fascinating. The scientists working on warp drive technology aren't trying to build faster-than-light spacecraft right now. They're trying to prove that controlled space-time manipulation microsec is possible at atomic scales. If they can warp space-time around a single atom, that proves the concept works. Scaling up becomes an engineering challenge rather than a fundamental physics problem. Recent experiments at several universities have shown tiny distortions in space-time using specially designed electromagnetic fields. The effects are measured in fractions of the width of protons, but they're detectable and reproducible. More importantly, they're consistent with the theoretical predictions of space-time manipulation. We're witnessing the birth of technology that could eventually allow spacecraft to travel faster than light without actually violating Einstein's speed limit. The implications extend far beyond propulsion, though. If we can manipulate space-time, we can potentially create artificial gravity fields for long-duration missions. We might be able to compress space around spacecraft to reduce journey times without requiring exotic fuel sources. We could even develop communication systems that operate outside normal space-time, allowing instantaneous contact across interstellar distances. But even if space-time manipulation proves impossible to scale up to practical levels, we have other options that are advancing rapidly. One of the most promising involves using the quantum properties of empty space itself as a propulsion medium. The vacuum of space isn't actually empty, it's filled with quantum fluctuations that constantly create and destroy virtual particles. Under the right conditions, these fluctuations can be harnessed to generate thrust. The physics behind quantum vacuum propulsion are still being worked out, but the experimental results are encouraging. Multiple research groups have measured tiny but consistent thrust effects when specially designed electromagnetic fields interact with the quantum vacuum. The forces are currently microscopic, but they demonstrate that the concept works in principle. What makes quantum vacuum propulsion revolutionary is that it requires no fuel whatsoever. A spacecraft could accelerate continuously for years or decades, limited only by the power available to run the electromagnetic field generators. Such a system could reach significant fractions of light speed while carrying substantial payloads, making it ideal for both robotic exploration and eventual human missions. The engineering challenges are substantial because quantum effects operate at scales where normal engineering principles don't apply. Creating the precisely controlled electromagnetic fields needed requires superconducting systems operating at temperatures close to absolute zero. Scaling up from laboratory demonstrations to spacecraft-sized systems presents problems that may take decades to solve completely. Yet progress is accelerating rapidly as our understanding of quantum mechanics becomes more sophisticated. Advances in superconducting materials, electromagnetic field control, and quantum measurement techniques are making previously impossible experiments routine. Multiple countries are investing heavily in quantum vacuum research because they recognize its potential for revolutionizing not just space travel, but energy generation and manufacturing as well. The timeline for practical quantum vacuum propulsion remains uncertain, but the theoretical foundations are solid and the experimental evidence is mounting. Some physicists believe we could see working prototypes within 20 years. Others think it might take 50 years to develop practical systems. The uncertainty reflects how revolutionary this technology would be if it proves scalable to spacecraft applications. Meanwhile, there's another approach that's been quietly advancing without much public attention. It's called solar system infrastructure development, and it involves building the support systems needed for interstellar missions right here in our cosmic neighborhood. Before we can seriously attempt to reach other stars, we need to establish the industrial capacity to build, fuel, and launch truly massive spacecraft. This means developing asteroid mining capabilities to provide raw materials without the enormous cost of lifting everything from Earth's surface. It means building orbital manufacturing facilities that can construct spacecraft components in the zero-gravity environment where they'll actually operate. It means establishing fuel production facilities that can generate propellant from resources we find in space rather than carrying everything from Earth. The economic benefits of this approach are staggering. A single metallic asteroid contains more platinum, gold, and rare earth elements than have ever been mined on Earth. The energy available from solar collectors in space, unfiltered by atmosphere and uninterrupted by night cycles, could power industrial operations on scales that dwarf anything possible on planetary surfaces. The low-gravity environment of space allows for manufacturing techniques and material properties that are impossible under terrestrial conditions. Private companies are already beginning to develop these capabilities. SpaceX's Starship is designed to carry massive payloads to orbit at costs that make space-based manufacturing economically viable. Asteroid mining companies are developing the robotic systems needed to extract resources from near-Earth objects. Solar power companies are designing orbital collectors that could beam energy back to Earth or power space-based industrial operations. The timeline for establishing serious space-based industry is measured in decades rather than centuries. Current projections suggest we could see operational asteroid mining within 20 years, with orbital manufacturing facilities following shortly afterward. Once these capabilities are established, building interstellar spacecraft becomes dramatically more practical because most of the materials and energy can be obtained in space rather than lifted from Earth's surface. This industrial approach to interstellar travel has another crucial advantage. It creates economic incentives that go far beyond scientific exploration. Space-based industry could generate enormous profits from asteroid mining, orbital manufacturing, and solar power generation. These economic returns could fund interstellar missions as side projects, rather than requiring dedicated government funding that competes with terrestrial priorities. The psychological impact of routine space industry also cannot be overstated. Once humans are living and working throughout the solar system as a matter of course, interstellar travel becomes a natural extension of existing activities rather than an impossible leap into the unknown. The cultural and technological infrastructure needed for interstellar missions develops organically as part of normal economic expansion rather than requiring special efforts that may not be sustained across multiple generations. But perhaps the most significant development in our path toward the stars isn't technological at all. It's the growing recognition that becoming an interstellar civilization isn't just an interesting possibility for some distant future. It's becoming an urgent necessity for ensuring human survival beyond the next few centuries. Earth faces multiple existential risks that could end human civilization regardless of our technological achievements. Asteroid impacts, supervolcanic eruptions, gamma-ray bursts, and the gradual brightening of our sun as it ages all pose threats that no planetary civilization can completely defend against. The only long-term solution is spreading human presence across multiple star systems so that local catastrophes cannot eliminate our entire species. This existential motivation is transforming how we approach interstellar travel. It's no longer a distant dream for future generations to pursue when they have nothing more urgent to worry about. It's becoming a critical priority for our generation to begin immediately, with the understanding that the work we do today will determine whether human consciousness survives beyond our current cosmic neighborhood. The shift in perspective is already influencing funding decisions, research priorities, and international cooperation in ways that wouldn't have been possible even a decade ago. Space agencies are increasingly framing their missions in terms of building capabilities needed for eventual interstellar travel. Private companies are investing in technologies that have obvious applications for escaping our solar system. Universities are producing graduates with expertise specifically relevant to interstellar mission design and operation. More importantly, public support for ambitious space projects is growing as people begin to understand the connection between space exploration and species survival. Polls consistently show increasing support for government funding of space programs, especially when the projects are framed in terms of ensuring humanity's long-term future rather than just satisfying scientific curiosity. The combination of advancing technology, economic incentives, and existential necessity is creating unprecedented momentum toward interstellar capabilities. Multiple approaches are being developed simultaneously, increasing our chances of success while reducing dependence on any single technological breakthrough. The timeline for serious interstellar missions continues to compress as progress accelerates across multiple fields simultaneously. Current projections suggest we'll see the first dedicated interstellar probe missions within the next 15 to 20 years. These initial missions will be relatively simple affairs, designed primarily to prove that controlled interstellar flight is possible and to gather basic information about conditions in nearby star systems. But they'll establish the technological and operational foundations for increasingly sophisticated missions that follow. By mid-century, we could see missions carrying advanced scientific equipment capable of detailed planetary surveys and searches for signs of life. By the end of the century, human interstellar missions could become feasible using technologies that are currently in early development phases. The transformation from a single planet species to an interstellar civilization could occur within the lifetimes of people alive today. The cosmic prison that has confined humanity throughout our entire evolutionary history is finally beginning to show cracks. The technologies needed to break free are being developed, tested, and refined by brilliant minds working in laboratories around the world. The economic incentives for space-based industry are creating market forces that drive technological advancement faster than government programs alone could achieve. Most importantly, humanity is beginning to understand that escaping our solar system isn't just about exploration and discovery. It's about ensuring that human consciousness, creativity, and culture can survive whatever cosmic catastrophes the universe might throw at us. We're not just reaching for the stars because they're there. We're reaching for them because our long-term survival depends on spreading beyond the single point of failure that Earth represents. The journey to become an interstellar species won't be easy, but it's no longer impossible. The physics work, the technologies are advancing, and the motivation is becoming undeniable. The only real question is how quickly we'll have the wisdom and courage to invest in technologies that will benefit not just our generation, but all future generations of humans who will inherit the galaxy we're preparing to explore. The answer to how close we are to escaping our solar system isn't measured in centuries anymore. It's measured in decades, and for the first time in human history, that enough that we can actually see timeline is short the finish line from where we're standing today. We're standing at the most pivotal moment in human history, where the impossible is becoming inevitable, and the timeline for escaping our cosmic prison is shrinking faster than most people realize. From ion drives that are already working in space today, to fusion rockets that could get us to nearby stars within a human lifetime, to light sails that could launch in the next 20 years, to exotic technologies like antimatter and quantum vacuum propulsion that sound like magic but are based on solid physics. Every single approach we've discussed represents a real path to the stars, not science fiction fantasies. The most remarkable thing isn't any individual technology, though. It's how all of these breakthroughs are happening simultaneously, creating multiple shots at success, while the economic incentives and existential necessity drive unprecedented investment and international cooperation. We're not talking about maybe reaching another star system someday if everything goes perfectly. We're talking about multiple missions launching toward different stars using different technologies, with the first detailed data from other worlds arriving while people watching this video are still alive. The cosmic prison that has held every human who ever existed is about to become humanity's launching pad to unlimited possibilities among the stars. Whether it's breakthrough starshot probes reaching Proxima Centauri in the 2060s, nuclear pulse ships carrying human crews in the 2090s, or technologies we haven't even discovered yet that could get us there even faster, one thing is absolutely certain. The question isn't whether we'll escape our solar system anymore. The question is which breakthrough will get us there first, and how quickly we'll have the courage to claim our destiny as an interstellar civilization.